Here we go. We're back to discrete probability distributions. We're about to go for the last group, and I think we should start out with today's bad pun. A guy entered 10 puns into a contest. When he went to check to see if any of the puns won, he found out no pun intended. Ha! Okay, so here we go. So we had been talking about binomial versus hypergeometric distributions. So let's talk first about some of the similarities between the two. The binomial, we sample n items, x of which are event A. Let's see, let's put those in place there. So here's our binomial, which we've spent some time with, and hypergeometric, which we've spent a little time with. So at any rate, the similarities are we're going to sample n items, and remember it's kind of the coin toss thing. So we're going to have n coin tosses, x of which are event A, call it heads, and the rest of which, so that's x of which, that's x is equal to 1, and there's our tails, which is n minus x. Those are event A complement. And order doesn't matter in this, right? Because we can have a head over in any other place and it doesn't really matter. So the differences, and that's the way it is also for the hypergeometric, of course. It doesn't matter which one we pick out. The differences are when we start picking out, for example, let's pretend these are tulip bulbs, and we'll have some nice yellow iris bulbs, or daffodil bulbs, I mean. So if we're picking out some daffodil bulbs versus picking out tulip bulbs, we know that once we start grabbing those bulbs, the Bernoulli property is no longer operating, because we're changing the odds when we start selecting one color or another. So hypergeometric, the Bernoulli property is not satisfied. They're not statistically independent. But and for the binomial, on the other hand, the Bernoulli property is satisfied, because when we flip a coin randomly, the next time it doesn't matter at all what happens. So binomial versus hypergeometric, if we're looking at those, the sample size, if the size of that sample space is large, and the property, if the sample space n is very large, then the probability actually becomes rather similar to the ratio of k over n. So k would be like the number of daffodil bulbs, where the maximum number that we have, over n. So in that case, then, we can say that it turns out that for large numbers, the binomial distribution sneaks perilously close to the hypergeometric distribution, and vice versa. So that's just kind of nice to know. They do resemble one another and actually devolve into one another when the sample space n is large enough. Now we've got our binomial versus hypergeometric. Who shall win? The binomial process, if we've got, basically what I tried to do here was to set up two problems that are really close to being identical, except one's going to be with binomial and the second was with hypergeometric, so you can see the differences. This one, I specify what the probability of a bad part is. Take a look, it's 0.05. And then I say, what's the probability that one of two parts randomly selected is bad? Okay, so this is always fixed, that bad part probability. If we look over here at the hypergeometric, on the other hand, suppose we've got, it says, two parts that are selected at random without replacement from a population of 100 parts where 5 are bad. Okay, we're selecting without replacement. That means once we take out a bad part, that we're changing the odds. So that immediately tells you that, well, Bernoulli does not live through this process, right? the probabilities are changing. So let's write down the formulas for each one of these. In this one, we're going to be using binomial, and we're looking for the probability of one bad part given that our n is 2. In other words, it's going to be 2 choose 1 is our set of combinations, and then 0.5, this is our p raised to the x power, and 0.95 is our q, which is 1 minus x raised to the n minus x power, which is also 1. And when we calculate that all out, it's 0.095. Okay, so that's a Bernoulli process and a binomial distribution. Now we've got our hypergeometric. So we're again going to calculate the probability of 1. So we're going to get 1 out of 2. And if we set it up as a hypergeometric, it's going to be the combinatorial of 5 choose 1. Right? We've got 5 bad parts, and we're choosing 1. And then the rest of that, remember we have to take care of the other combinatorial in the top, and we're going to have, well, let me write this, the whole dividing number of combinatorials is 100 choose 2, and then the other on top is 95 choose 1, right? So in other words, we have one bad one and we have one good one, and that's out of the total combination. When we calculate that out, it turns out to be 0.096. Very close, not quite the same as binomial, but very close, and that's what we would expect it to be. I think if you contrast these two problems and think about them, you'll find that this can help clarify the difference between these two different distributions. So now, what happens if we have a problem like this, where we have guinea pigs that have the unfortunate habit of having offspring that can have multiple colors, which can skew our whole statistical probability sets of calculations, because we can now have more than just 2 possibilities as far as our outcomes, which means Bernoulli is not alive. So the guinea pigs can produce either red, black, or white offspring, and normally they have sort of a 50% chance, or 8 out of 16 of having red, and 4 out of 16 of being black, and 4 out of 16 of being white. We want to find the probability that among 8 offspring, we'll have 5 red, 2 black, and 1 white. And I ask here, why are binomial, negative binomial, and hypergeometric not appropriate? Well, I pretty much already answered that. It's because we've got 3 different possible outcomes. That's the real issue here. Let's go back and let's have just a little bit of a side note here. Let's say that we have a set and it has n elements of a certain type. Okay, and so you can think of it as our n elements. Okay, I do not play football, but we shall pretend that I do. Okay, so we've got, let's say n is equal to 15, and these are all football players. So we're going to say that x1 elements of type 1, that means, so we're going to have 5 x1s are freshmen, and we'll have 9 x2s are seniors, seniors, and that leaves 1 lonely x3 as, well, there's only 1 actually, so we'll take care of that, is a sophomore. So all of them total up to 15, right? And we've got 5 different x1s, 9 x2s, and 1 x3. The trick is when we line these guys up. Okay, so we're going to have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then our last one, there's our last little one there. If we're trying to figure out how many possible ways to rearrange this set of a team, which is, I think, bigger than a team usually is, who knows? Okay. You can laugh at my lack of football knowledge. Okay, so anyway, if I switch some of these seniors, the red ones, if I swap this guy with this guy, we don't care. I mean, it's the same from our perspective. I mean, if we swap these two, it might be different, right? But if we swap these, it's actually the same. So anyway, how do we capture a combination? Right, we already know that if we had the permutation of all these, if we switched anything, it would make a different permutation. But this one is kind of like a partial combination, because whenever we switch somebody of the same color, it doesn't matter. It's considered the same. But if we switch somebody of a different color, it isn't considered the same. So the way we do this is we first switch to a darker pen color, so that it looks a little better. Okay, let's take this kind of army green here. Okay, we do a combinatorial where we have our total n, and then we have with x1, x2, and all the way out to xm, and that is written like this: n factorial. And we divide out each one of those possibilities. This is kind of like that r factorial. We divide out each of these possible local ways we can rearrange, like these colors, you know, all the red ones. We divide out all of those, and by dividing out that from the n factorial, we have the combinatorial for this set that has multiple elements of given types. So we also note that n is equal to x1 plus x2 plus plus xm, and order matters among dissimilar types of elements, but it doesn't matter among similar types. Okay, so we've kind of made that clear as our little side note, and you probably, knowing what we did with the hypergeometric and with the binomial, you might have a sneaking suspicion that the binomial was actually a special case of something called the multinomial, and in fact that's what we're going to see coming up here. But first, how many different ways can you arrange 2 apples, 3 oranges, and 4 mangoes? And this is a good question, especially if you like mangoes. So to work this problem, we would just set up a combinatorial. So we have 9 altogether, and we're choosing 2, 3, and 4. So we'll have 9 factorial on the top, and we're going to get rid of all of our little extra combinatorial or extra permutations that didn't really matter. 2, 3, 4 factorial, and that turns out to be 1260. So voila. Okay, now we'll get to the multinomial distribution. So for the multinomial, we will consider a discrete random process that satisfies the Bernoulli property with k outcomes, a1, a2, whatever. So all of them are mutually exclusive, and those a1s and a2s, all those elements add together to form the whole sample. So let's let pi be the probability that event whatever AI occurs, that we have freshman or something like that, and I is equal to 1, 2, up, all the way to k, and define the k random variables. So we'll say xi is equal to the number of times event AI occurs in n trials. And of course I goes all the way from 1 to k, and we can say so this is a little bit like saying, find the probability that among 8 offspring from the guinea pig, 5 will be red, 2 black, and 1 white. So that's essentially, we're saying xi, what's the probability that we're going to have 5 is the number of times of a red, so it would be like 5 red offspring occurs in 8, right? Or we can say 2 black, so we could have 2 is the number of events of black occurring in the 8 trials, right? So that sort of thing. So then probability of x1, x2, well, I'm going to say just all the way up to xk is equal to that combinatorial of x1, x2, all the way up to xk, and times the probability of the first one raised to x1 times the probability of the second one, x2, all the way up to the probability of k raised to the xk, and where x1 plus x2 plus xk is equal to n. Okay, so we add those all up, and the probability, all of those probabilities plus pk is equal to 1. So there we go. There's your multinomial distribution. So, well, I guess it's written again right there. So, okay, it's very important for you to note that statistics play an important part in genetics. So, for an example, statistics show that numbers of offspring is an inherited trait. So if your parents didn't have any kids, the odds are you won't either. Okay, now on to more painful punishments. Let's see. Okay, so according to genetics theory, a certain cross of guinea pigs will result in red, black, and white offspring in the ratio of 8 to 4 to 4. So we've kind of already seen this. Find the probability that among the 8 offspring, 5 will be red, 2 black, and 1 white. So this is, in essence, we'll write down the multinomial here so we've got it handy. x2 and all the way up to xk, p1 to the x1, p2 to the x2, and to the pk to the xk. So if we just plug our numbers in, we know that n is 8, and we've got x1 is 5, x2 is 2, x3 is 1. So we just need that combinatorial. And so we can write that as 8, and then 5, choose 5, 2, and 1. And then it'll be the probability of the first one is going to be 1/2, right? Because 8 out of 16. So it's 1/2 to the 5th power, because that's x1. And then it's going to be 1/4, right? Because it's going to be, that's from that 4 raised to the 2's power, because there's only 2 little puppies. And lastly, it will again be 1/4, and it's raised to the 1 power, so we just won't even bother to write it there. And if you remember, this is just going to be 8 factorial over 5 factorial, 2 factorial, 1 factorial. And when you calculate this whole thing out, it will become 21 over 256. Voila. Okay, so we've got that. Now let's work another problem, or let's see, do a little bit, we'll actually do a little bit of exploration. The binomial distribution, as it turns out, is just a special case of the multinomial, and in that particular case, it's the k is equal to 2. So notice that with the multinomial distribution, it has k random variables, x1, x2, blah, 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 all the way to k. So before we had 3 different colors in our guinea pigs. So our current definitions for expected value and variance actually won't work in this case. But lucky for you, we're not going to learn about that now. We're going to learn about that later when we study processes with multiple random variables. So what are our distributions so far? Let's stop and take a look. One thing I do want, I had a little trouble when I was creating this thing, so this should not be there. The little bar looking like a divider, it's n, choose n with no ratio or anything like that. So I just want to cross those out. Okay, but otherwise this is just fine. So we've got multinomial, right? And that's the kind of thing where, well, your guinea pig is, instead of flipping coins of one color like the binomial does, so I mean it's like you've got either heads or tails, but now you've got babies that can be 3 colors, so you can throw coins of 3 colors in essence, and that's what the multinomial does. This is coins of only 2 flavors, right? Heads or tails. Negative binomial says it's the kind of thing where it's like almost the binomial, except that you're trying to figure out the probability where some kind of event occurs for like the 4th time, that you threw tails for the 4th time out of 20 throws or something like that. And the special case of that is geometric. That's just where it occurs for the 1st time. And lastly, we've got hypergeometric, and that's usually a sampling kind of thing, where you're sampling without replacement. And that's where poor Bernoulli dies, because selection process influences the odds of what remains. So let's go on a little bit, and let's consider a CNC lathe problem, which produces a part of a diameter. So we define events. Let's define events where we've got A1, where the diameter is okay. A2 is where it's just a little bit too big. It's like the porridge with too hot or something like that. Okay, and then the other one where the diameter is too small. And the nice thing about this is something that gives us the ability to look at this from the perspective of not binomial, but rather more like a multinomial problem. What we're really looking for is, well, let's write our combinatorial here, of n, and we're choosing x1, x2, and x3. Probability 1, x1, probability 2, x2, probability 3, x3. It's pretty clear that this is going to be a multinomial. That's exactly what we're looking for, and all we have to do is plug in numbers. What is our total? The total number of parts? 12. So we stick a 12 in there. What is our x1? x1, they're saying, well, look, they're saying 2 will be too large and 1 will be too small. So what does that leave? There's some left over here, and that means there's 9 that's x1, and we'll call that okay. x1 is going to be okay, and there's 9 okays. x2, let's make that too big. So this one's 9, this one's going to be 2, and this one's too small, and there's 1. Okay, so what's the probability of it being okay? Well, let's see, that's 0.93. So we'll put what? 0.93. And what was x1? Right here. That's where we've got it right here, is x1 is 9. So we raise that to the 9th power. Probability that the part is going to be too big is 0.04. So we'll write 0.04, and we'll raise that to the x2, which is 2. And lastly, we've got 0.03, right from right here, 0.03, and we'll raise that to the 1 power. And remember that this, you compute it all as 12 factorial over 9 factorial times 2 factorial times 1 factorial, and then multiply this all out, and you will get 0.016. So that's our problem. Now let's go on and do another problem. So if we look at the hypergeometric distribution and we think about it a little bit, what we'll find is that, okay, we could have selected 4 daffodil bulbs and 5 tulip bulbs from this, and we could have gotten a hypergeometric distribution. In other words, when we select one, we'll change the odds. But just as we had more than 2 flavors available when we started talking multinomial, and the many colored offspring of guinea pigs, likewise for the hypergeometric, we can have more than 2 flavors, right? We can have yellow and, well, I think, come to think of it, I have it here. Yes. Okay, we could have something like also 3 hyacinth bulbs. And actually, hyacinths are some of my favorite flowers. So what is the probability I planted, for example, 2 daffodils, 4 tulips, and 1 hyacinth bulb? How do we handle that with a hypergeometric distribution? Well, you've got to get something a little bit more general, and because it's more general, we call it the general hypergeometric distribution. And for that one, all we need to do is write down this xi means the number of times that some event is selected. So we could say, what's the probability, for example, that we will select 2 daffodil bulbs and a certain number of these remaining other bulbs, out of whatever clutch of numbers that or bulbs that we're selecting. And if we do that, we can say the probability of getting this particular setup, like of getting 1 daffodil bulb out of, see, look at that, 1 out of what? We've got 4. Out of 4. And maybe 2 of the tulip bulbs out of, we've got 5. Notice how I'm selecting the x2 and the k2. You want to really see exactly how I'm figuring that out. Remember, x2 is what I'm actually choosing. The k's are the maximum that we have available. And then finally, so we could say all the way up to, I don't know, select 3 out of the 3 bulbs that we have right there. And then this, the big N is the total number of bulbs. So in this case, it would be 1, 2, 3, 4, 9, 10, 11, 12. Okay, so that's 12 bulbs. And then N, how many did we actually choose? We chose one, one of these kinds of yellow bulbs, 2 of the red bulbs, so that's 3, and then 3 of these, so it's 6 altogether. So this is how we set up something with general hypergeometric distributions. The only confusing part is, what's a k and what's an x. And once you figure out k is like the upper limit of each one, and x is what you actually choose. And then again, the big N is the total number, and the little n is how many total that you've chosen. Once you get that figured out, you're golden. You can plug virtually anything in with a general hypergeometric distribution. Oh yes, does Bernoulli rule? Is it statistically independent? Let's see. No, it's not statistically independent. That was supposed to be sort of a lethal sound on poor Bernoulli, because once you select anything out of there, you start distorting the odds, changing the odds. And so Bernoulli does not apply in this particular situation. Now I want to give you an example of general hypergeometric, and we shall use pumpkins in keeping with the theme of this video. So here you see 9 pumpkins. And just for convenience, I have numbered the pumpkins, right? So how many permutations can I have if I select 6 pumpkins? Let's see. It's 9 choose 6 permutations, so that would be 9 factorial over 9 minus 6 factorial, which is the same as 9 times 8 times 7. So we pick the first one, we've got 9 choices. Second one, we've got 8 choices. Third one, we've got 7 choices. All of that amounts to 60,480. So that's the number of permutations we have of pumpkins, 9 pumpkins if we choose 6. But you know that a lot of those permutations are the same sort of thing. We'd have 1, 2, 3, 4, 5, 6 would be pretty much the same as 1, 3, 2, 4, 5, 6. So we could reduce the number into the number of combinations, 9 choose 6 combinations, right? And the way we do that is we almost use exactly the same formula as before. It's 9 minus 6. But we have to reduce it further by using 6 factorial, or dividing by 6 factorial. That reduces it to the number of combinations. So we're not duplicating the same rearranged numbers. And that gives us only 84. So if we wanted to, we can rewrite this as 9 choose 6, right? And that's only 84. So we can say that there are 9 choose 6 or 84 different combinations if we chose 6 of the 9 pumpkins. Now let's say that we wanted to figure out the probability that we would choose any of the 6 out of 9 pumpkins. Well, our probability is just, well, let's see, we can say we've got 9 pumpkins. We're going to choose 6 of them. The number of combinations of that are possible is 9 choose 6, 84. So basically the probability that we would choose any of the 6 possible combinations of these 9 pumpkins is 100%. So that seems pretty obvious. What if we try something different? What if we, instead of this one normal orange pumpkin, let's say that we erase that normal orange pumpkin and we say that this is going to be a black pumpkin. So now I've got 8 orange pumpkins and 1 black pumpkin. I want to choose that black pumpkin for sure. And the other 5 pumpkins can be these orange ones. So it turns out there's 1 black pumpkin and there's only one way to choose it. so I want to choose it. And then I can have, of the remaining 8 pumpkins, I want to choose 5 of those orange pumpkins. So there's 8 orange ones, I want to choose 5. So in other words, now our probability has been reduced because we have to choose this one. So it turns out that this reduction makes it so that we've got 56, that's this 8 choose 5, times 1. So now we only have 56 out of the total probabilities of 84 available. So you can see because we have a different type of pumpkin here, we've reduced the number of possibilities of combinations that are available if we mandate that we have to choose this one black pumpkin amongst all of our choices. But let's change up things a little bit more. Let's change some of these into green pumpkins. So now you see what we've got. We've got 5 orange pumpkins, 3 green pumpkins, and 1 black pumpkin. Let's say that I wanted to, now I'm still going to choose 6 possible pumpkins. Let's say that I want to choose 3 of these orange pumpkins, 2 of the green ones, and we're still going to pick a black pumpkin. So that's a total of 6. What are the possibilities? Well, let's see. I've got to have 5 choose 3 of the orange pumpkins, 3 choose 2 of the green pumpkins, and 1 choose 1 of the black pumpkins. If you multiply that all out, you will end up with 30 different possible combinations of these particular types out of a possible total of 84 different combinations. So you can see the probabilities change depending on what you pick, and this is a good example of the general hypergeometric distribution and how you can use it. So keep your focus now. Here we go. The distributions we've got so far are, number 1, multinomial. So if that's multinomial, does Bernoulli live? Well, we know that the odds are not changing in this particular case, and it's independent. There's only 2 possible outcomes. Order doesn't matter, and so he stays alive. That was indicating he stays alive. And so order doesn't matter, and number of outcomes, we've got k possible outcomes for multinomial, and the number of trials, we've got n trials. Okay, now here, so that was multinomial. Binomial, does Bernoulli live? Let's see, do the odds change? No. The odds do not change with binomial. You flip coins, they stay the same, so he stays alive. Does order matter for binomial? Actually, order doesn't matter at all, so we'll knock it out. Number of outcomes for binomial? 2, right? It's either heads or tails. And what about, oops, maybe hard to see, but over here, the number of trials is n. And so there we're all done with binomial. So now let's look at negative binomial. Do the odds change? Do P and Q change? That's supposed to be applause there. No, they do not change, so Bernoulli keeps alive. And how about order? Does order matter for negative binomial? Yeah, it kind of does, because the order matters on the very last one. So we say, yes, order matters, and that thumbs up is different than order doesn't matter, where I crossed it out. So, and let's see, and oops, my thumb disappeared. Oh, that's because I went back. Sorry about that. Okay, so how about the number of outcomes? What's the number of outcomes for negative binomial? 2. So it's 10th person randomly interviewed, has a dog or doesn't have a dog, right? And number of trials, well, doesn't really, we don't think about it that way. We think about it as the trial number as being X, right? The 5th one to own a dog. And for geometric, it's going to be pretty much the same as for negative binomial because it's a special case of negative binomial. And does order matter? Yep, because it's going to be, well, the trial number where some event occurs for the first time. And the number of outcomes. What is the number of outcomes? 2, again, because either you passed the test or you didn't pass the test. And lastly, the number of trials that you might have. Well, again, it's just like for negative binomial. We say the trial number is X, right? The trial number where you first passed a test. So now let's go, and again, we'll cross this little part, this bad part right out of this, right? Okay, see that you didn't see that. So now let's go to hypergeometric. Does Bernoulli live for hypergeometric? Remember that the odds change for hypergeometric. So he does not make it. Okay, so there we go. How about order? Does order matter for hypergeometric? No, because it doesn't matter how you pick it out, pick jelly beans out of a jar. Okay, how about the number of outcomes? Number of outcomes is 2 for hypergeometric. And the number of trials is n. Okay, what about general hypergeometric? What's the difference? Well, we'll see. Does Bernoulli live? No, he did not live. How about order? Does order matter? No. And let's see, the number of outcomes is k, right? We've got k possible outcomes. And that relates to, you know, we may have 5 red guinea pigs, 3 maximum blue guinea pigs, however you want to choose that. But that's what that k indicates. And lastly, we've got the number of trials over here is n. Oops, sorry about that. The number of trials is n, and then the total number is the big N. So that was my way of trying to quickly go over all of the distributions that we've covered so far. So now let's go back to doing another problem. Let's suppose that there are 65 cars in the parking lot, 20 of them are Chevys, 15 are Fords, 17 are Chryslers, and 13 are Hondas. So if we take 10 cars at random for emissions testing, what's the probability that we've got 4 Chevys, 3 Fords, 2 Chryslers? That is a Michigan endogenous expression. And 1 Honda, and then 1 is a Yugo. Well, haha, there's my Yugo. Actually, just ignore that because that's sort of a null set. So we will pretend I didn't say that. Okay, so let's see if we can calculate this. So we're essentially saying the probability that we're grabbing 10 and then we're going to get 4 Chevys, 3 Fords, 2 Chryslers, and a Honda. And if we write it all out, the general hypergeometric is just going to be a combinatorial of, let's see, well, what is our K for the first one, for the Chevys? 20 is our K, right? That's the maximum that we've got. And we're choosing 4. And then we've got 15 Chrysler, and we're choosing 3. So here's where the 15 came from, right up there, and we're choosing 3. Okay, and lastly, we've got, well, not quite lastly, we're now on to the Chrysler, and there's 17 of those, and we're choosing 2, and 13 are Hondas, so that's our K, and 1 is what we're choosing. And now we need to divide that by big N over little n, And our big N is the sum of all of the different kinds of cars we've got, which is 65. And we're choosing from that 10. And when you calculate that all out, you get, well, actually it turns out to be 4845 times 455 times 136 times 13. Oops. 13, and divide all of that by 1.79 times 10 to the 11th, and that turns out to be about 0.022. So there we go. That's what the probability would be, and we're using general hypergeometric to calculate that.